So we're going to solve logarithmic equations here. And when you're solving logarithmic equations, there's going to be two different methods. I'll call them method 1 and method 2. I'm not going to ask you for these things by name, so we'll just leave it generically like that. But the first one is this. If you have the log of something, say the log of A equals the log of B, leave a little bit of room for the base. But if you have the log of A equals the log of B, then A equals B. Basically, you can get rid of the logs. Now, it's not that you're canceling logs on both sides. It doesn't work that way. I will show you exactly what's happening, but you're not canceling the log on both sides. That's for sure. Now, even though it's not written, it's understood this is true for any base. So we'll just, again, write the generic base B for both of these. As long as B is positive and not equal to 1, we're okay. That's the first method. The second method is doing something we've actually done before. If we have the log base B of x equals y, well, that's a little different. Why is this a little different than the first method? Yeah, I don't have a log on this side, right? Here, to use this idea, I have to have logs on both sides. A log of something equals a log of something else. Then you can get rid of the logs. But here, well, let's see what we've done before. We've rewritten this using exponents. So equivalently speaking, what would this be using exponents? Perfect. The base to this power equals this, so b to the y equals x. Perfect. So those two ideas are going to solve pretty much all our equations here. Now we're going to have to extend them a little bit, but this is going to get everything done for us that we need. We'll start with problem number 44. Log base 4 of 2x minus 1 equals 3. So which method are we going to use to solve here? Is this a method 1 problem or is this a method 2 problem? Method 2, because you don't have logs on both sides. So does someone want to rewrite this using exponents for me? Four to the third power equals, perfect. 4 to the third equals 2x minus 1. 4 to the third, hopefully you can get that off your calculator, or at the very least, the left-hand side board. That's 64. Well, this isn't too bad. Add 1, 65 equals 2x, and then divide by 2. So 65 over 2 equals x. Nice. 32.5. Now there is going to be something that eventually we're going to have to take care of and be a little bit more exact about, and that is, with these types of problems, you have to be careful with your answers. You have to make sure that even though you might get a nice answer, that when you put it back into your problem, you don't get a negative number. You can't take the log of a negative number. And it's kind of a little test or reminder for you on that. Try taking the logarithm of 0. See what happens when you take the log of 0. Is your calculator liking you when you take the log of 0? No, it certainly doesn't. So y equals log x. And let's see up here. There we go. So let's take a look at what's going on. Now, when I take the log of 0, I get what's called a domain error. It's because log is not defined at that point. So, where is log defined? Well, let's remind ourselves of this by looking at the graph of the logarithm. Now, this this graph gets closer and closer to the y-axis. Do you think it ever touches the y-axis? No. It's just kind of like the exponential graph. Never touch the x-axis. This never touches the y-axis. In fact, it doesn't exist to the left of the y-axis. You can't take the log of a negative number. You can't take the log of 0. You can only take the log of a positive number, and that's it. So when you're looking at your solutions, you got to make sure that when you put this in, it doesn't give you a negative number. You can't take the log of a negative number. Now notice what I'm not saying. I'm not saying that this number itself can't be negative. I'm saying you can't take the log of a negative number. And hopefully you understand the difference. Let's try a different one. Problem number 48. If you gave me 32.5, that'd be fine. I mean, I like fractions better usually, but unless I specifically say I want it as a fraction, if you gave me 32.5, that's fine. Okay, thanks for the question. Let's take a look at problem number 48. Log of 1/5 x equals -3. Method 1 or method 2? Method 2. Good job. Now, it's not really written, but what base is understood to be here? 10. So see if you can't rewrite this using exponents. We're going to solve it. We're actually going to try and come up with a fraction. Let's see if you can't rewrite it using exponents first. Katie, want to give that one a shot? What's this look like if I rewrote it using exponents? Someone want to help? Always start with the base to this power equals that. So there's a couple voices back there helping out. Thank you. 10 to the -3rd equals 1/5 x. Let's clean up 10 to the -3rd real quick. That'd be 1 over 10 cubed. What's 10 cubed? 1,000. So it's really 1 over 1,000 equals 1 over 5 times x. Now, some of you might just do this completely on your calculator, say, okay, 10 to the -1/3, that gives me 0.001, divide by 1/5. But let me suggest a different way to finish solving here. I would just multiply through by 5 on both sides, or 5 over 1 if you prefer. Yeah, just times it by the reciprocal, exactly. And on the right-hand side, that cancels. And on the left-hand side, 5 goes into 1,000 200 times. If you gave me the decimal value of 0.005, that's fine as well, unless I specifically ask for fractions. Okay, not so bad. Let's check it. In this one, we can check it pretty easily because this is log base 10. It's kind of built in to your calculator. So let me get rid of this. I'll do log of 1/5. So parentheses 1 divided by 5 times 0.005. And if I did things right, I should get -3. Perfect. So it checks. Zarima, you looked a little unhappy with that one. You're like, wait a minute, what kind of hocus pocus you're pulling? Down here, 1/200th is 0.005. So I just put it back in here. Really, all you have to do is make sure that you get a positive number here. And 1/5 times 0.005, I don't know what that is off the top of my head necessarily, but I know that it's positive because you have a positive times a positive. And that's really the bottom line that you have to check for. Okay? So we actually went a little farther. We actually proved our answer was right. You're welcome. Let's try problem number 50. Log of 3x plus 5 equals a log of 2x plus 6. So this is problem number 50. What method am I going to use in this one? Good, the first one. All right. We're using the first one because you have the log of something equals a log of something else. So you can get rid of the logs, right? That is, you can just write A equals B. Now I'm going to leave a little space here and show you mathematically what allows you to get from here down to here. But as far as getting this problem right and doing it, really, you can just skip down to 3x plus 5 equals 2x plus 6. Perfect. And you can solve here and get full credit. Nothing wrong with this at all. So I'll subtract 2x from both sides, and I'll also subtract 5 from both sides, so that I get my x's over here and get my constants over here. Elena, what comes out of this? Sure, x equals 1. And that's it, you're done. Now you should go back and make sure that this actually doesn't create any problems. And if I put a 1 here, okay, I get 3 times 1 plus 5 is 8. So I get the log of 8. On the right-hand side, 2 times 1 is 2 plus 6 is 8. So I get the log of 8 equals the log of 8. So it checks. X equals 1 checks. I want to be clear, though. It's okay to have a negative answer. It's not okay to take the log of a negative answer. If this was negative 1, 3 times negative 1 is negative 3 plus 5 would be 2. And you're okay there. So there's nothing wrong with taking the log of 2. There'd be nothing wrong with a negative number. It wouldn't check on the right-hand side. It wouldn't get, these two things equal like I did with 1. It gave me log of 8 equals log of 8. And that's a nice clear check. But what you're looking to make sure doesn't happen is you take the log of a negative number. Are we okay with problem number 50? Because I can. Because it makes it a solvable problem. I'm using this idea that I gave us back here with method 1. If you have log of something equals log of something else, you can get rid of the logs. Now what you have to be careful of is you can't do this just any time you want. You have to have the log of something equals the log of something else. So you got a great question here. Let me see if I can't find an example. Yeah. So problem number 78. Let's take a quick look there. Problem 78. You've got the log of 3 minus 2x, log of 3 minus 2x, minus the log of x plus 9 equals 0. Can I just get rid of the logs? It's because of the minus sign. It's because to get rid of the logs, what do I need? I need to have the log of something equals the log of something else. So I don't have that right now. I've got log of something minus log of something equals 0. I can't do it. Yeah. Beautiful. So if I add this to both sides, in other words, if I move this to the right-hand side, then I'll be in good shape. Then I'll be okay. Great question. What happens to the sign? When it changes sides, it changes signs. So that negative is going to become a positive, and over here, 3 minus 2x equals log of x plus 9. Now I can get rid of the logs. If on your paper, if I see you get rid of the logs here, even if you get the right answer, you're going to lose some points because you can't. It's, you get the right answer, well, you got lucky. But the real way to solve this is to move this to the right-hand side. And now I can get rid of the logs. I'm going to leave a little space here. I'm going to give 3 minus 2x equals x plus 9. Okay. Actually, I'd add 2x to both sides because it puts the side, x is on the side with the larger one, and then subtract 9 from both sides. Negative 6 equals 3x. So what does x equal? Negative 2 equals x. Do I have to throw this out because it's negative? No. The log can't be negative, but let's see. Let's check it. Let's check it. So if I put that up here, then I end up with the log of 3 minus 2 times negative 2 minus the log of negative 2 plus 9. So let's see, that's a negative 2 that I'm going to squeeze in here. A negative times a negative is positive. So I get log of 7 minus log of 7. I don't need to type that into my calculator to see that log of 7 minus log of 7 is 0. All right, it's nice to see that it really checked, but at least make sure that you're not going to get the log of a negative number. So that was a great question and great example. So hopefully you got a couple things out of that one. Let's keep going. Let me go back up here and show you why and how these logs cancel. This is not for the faint of heart. If you're already confused by this stuff, maybe close your eyes, check your text messages real quick, etc. But don't look if you're afraid of being confused. If you do this on a test, though, if you do show me the correct work here, I'd probably give you an extra credit point, because that's really impressive if you can get this. Let's start here. What basis is understood to be here with the logarithm? 10. All right, so we get 10 on both sides. Now, earlier you saw when we were doing our exponential equations that log base 8 and 8 to some power, they cancel each other out, right? Because they're inverse functions. That works both directions. So if I make 10 the base of both sides of this, so 10 exponentiated to the log base 10 of 3x plus 5 equals 10 raised to this power log base 10 of 2x plus 6, the exponent and the logarithm cancel each other out. So you're really raising both sides to the power of 10, and these cancel each other out. That's what allows you to get from here to here. So that's the missing step. You don't have to show that. You can just jump right here to here. These two operations cancel each other out. Okay. The property that I'm using is this one. B to the log base B of x equals x. These two operations cancel each other out. This is the equivalent of taking the cube root of x cubed. These operations are opposite operations. They're inverse functions. So when you do that, they just cancel each other out and you get back to where you started. And that's what's happening here. This operation, 10 to the power and log base 10 are opposite operations. So what pops out of it is this and this. 3x plus 5 and 2x plus 6. Yes? You have to use the log same base on both sides. So if you had log base 5 and log base 6, you'd have to do something else entirely. It's not something that I think I would throw at you in a test. I don't think you'll even see it in the homework problems, to be honest. So, I mean, the same thing is true in here. You would be doing 10 to the log base 10 of 3x minus 2 equals 10 to the log base 10 of x plus 9. So that's that missing step. So if you put that in, that's a bonus. That's nice. Yes. So as long as the bases are the same, you can use that method. That's this right here. The bases have to be the same. That's the only reason that this works. All right, good questions. Let me keep going. Let's try problem number 52. ln of x squared plus 4x equals the ln of x squared plus 16. It's not really written, but what base is understood to be here? E. Log base e of x squared plus 4x. In fact, there's really not much benefit to rewriting it like this. I'm just reminding you that the bases are the same. But yeah, you can get rid of them, right? Now, there is that step that you can write, but I want us to just focus on the math here. So I'm going to leave that step blank here. You can fill it in if you'd like to. X squared plus 4x equals x squared plus 16. Well, that's not too bad. Let's solve. What do you need to do to solve here? I'd probably subtract something from both sides. Does this make life easier? What does x equal? Yeah, x equals 4. Cool. But please, when you're doing these problems, you got to go back and check them. So let's take a look at how that would work. If you check them, then you're going to get full points. It'd be the log of 4 squared plus 4 times 4, and the log of 4 squared plus 16. Now, the big thing is that they're both positive, right? But there's a bonus here. You get ln of 32 equals ln of 32. So not only are you proving that you don't have an extraneous solution, but you're proving that it actually works. This is actually the solution. What if I gave you a problem like number 54? Log of x plus log of x plus 9 equals 1. Uh-oh. It's a good question. We can't distribute. There's no property of logs that allows us to distribute here. Well, adding 1 is not going to work. Let's tell you what. Let's decide what method we're going to do first. Do you think we're going to be able to do method 1, or we have to do method 2? Probably method 2. And the reason we're going to do method 2 is because not all of these terms are surrounded by a log. I don't have logs on all these terms. But Method 2 still has its problems. I need to get log of something equals 1. And the question is, what's that something? Yeah, please.
So going back to the other problem where we had to put it on the other side, not that one, we had to get the log on the other side. Like a subtraction.
Oh, 78, yeah.
Like that, yeah.
The nice thing about this one is that all these terms had a log. Whereas this one, I got a 1 here, and that's not part of a log.
There was 0.
Well, there's a 0, but we kind of got rid of the 0 by moving this to the other side, right? If I moved this to the other side, I'm still stuck with the 1. I can't get rid of that 1. So it's a little different. Now, tell you what we can do, though. We can use our properties of logs. Last week, we spent a lot of time using properties of logs. This kind of reminds me of my little log cabin gimmick thing, right? You've got the log of something plus the log of something else. And in case I'm not being specific enough, let me actually write this down. It's our product rule. Log of A plus log of B is log of A times B. Now, last week we were mostly using it in this direction, right? The log of a product became the sum of the logs. This time we've got to use it in the opposite direction. We're going to start out with the sum of the logs and turn it into the log of a product. Have you raced ahead of me? What am I going to write here? The log of what? X. Perfect. Thank you, ladies. X times x plus 9. So, and just to be clear here, let me put parentheses around this. We're taking the log of that. So that's your, basically your A times B. Let me do something else here. Let's distribute that. That's going to be x squared plus 9x. Karen A., what base is understood to be here?
I'm guessing 1.
One more time. 10. Thank you. So log base 10 on both sides. What method are we going to use now? Method 1 or method 2? 2, right? So we've got the log of something equals a number, right?
Why is 10 there?
It's a good question. How do you know to put the 10 there? Yeah. Log is understood to be base 10. Okay? So if nothing is written, it's understood to be a base 10. Just kind of like square roots. You know, if I don't write anything, it's understood to be a 2. But we typically don't write it. We just simply write square root of 25. Can someone rewrite this? Always start with the base. The base to the right-hand side equals this. So 10 to the first power equals x squared plus 9x. Nice. Now what? Let's move the 10 to the other side. I get 0 equals x squared plus 9x minus 10. So we'll use the quadratic formula, right? All right, maybe not. I was waiting for somebody to react. Thank you. X and an x, plus and a minus. Throw in two numbers there that work. Two numbers that multiply to negative 10 and add to positive 9. Negative 1 and positive 10. The larger one has to have that sign. What are my two solutions? Oh, thank you. I was about 2 more seconds. I'm going to say, take 2 points off your paper. You have to check it. And we don't get really too far in checking this, do we? When you go back up to the original problem, what happens? Yeah, you're taking the log of a negative number, right? The log of negative 10. Well, as I showed you earlier, the graph of the logarithm does not exist for negative numbers. It's only positive numbers. So that solution gets thrown out right away. Well, let's hope that 1 works, right? Well, at least 1 doesn't give us anything negative, right? Log of 1, we're okay there. Log of 10, we're okay there. So hopefully 1 works. Well, actually, 1 you can prove that it works. Let's take a look here. Let's check it. It'd be the log of 1 plus the log of what? Which is 10. Does anyone remember what the log of 1 is? What power of 10 gives me 1? 0. What power of 10 gives me 10? 1. So it actually does work pretty nicely. But yeah, at the very least, make sure that you're not going to take the log of a negative number. That's the minimum that you should be doing. Yes?
So for the check, just to clarify myself, like when you are doing it, like you're taking the log of each of the answers, adding or subtracting or whatever, like the sign says to do.
Yep.
And then like those answers, like the 0 and 1.
It should work in your original equation.
Okay.
Yeah. Now that may take different forms, like problem 78. We had what, the log of 7 minus a log of 7.
Yeah. So do we have to, let's say unserved, there's just 1.
Yes, there's just 1. Now, for myself, it's enough for you to circle this and throw a slash through it to say, okay, you can't use that answer. Does anyone remember the fancy word for it? Extraneous solution. So we had extraneous solutions earlier in this course. This is another one. Let's try another one like that. Problem number 56. Log base 2 of x minus 7 plus a log base 2 of x is equal to 3. Do you want to try this one? Maybe help each other out. I'll walk around, try and torment you, help you as well. Give this one a shot, but help each other out too. If you're getting stuck or once you get the answer, check it with your neighbor. Help each other out. If you're at home, try it yourself before you unpause. long time ago. Wow, that's nice. All right. Okay, so like the last problem, we're going to bring these two together and then use method, what is it, 2? Method 2, thank you. So it's going to be log base 2. I'm going to have two things that multiply each other. This and this. So log base 2 of x minus 7 times x. So here's the x, and here's the x minus 7. I'm taking the log of that whole thing. So if you want, you can put extra parentheses around there. I still have the 3 on the right-hand side. So this is log base 2 of x squared minus 7x equals 3. Okay. Are we comfortable with this so far? Now the idea is to rewrite this using exponents. So let's see. I'll do it this way. It's going to be 2 raised to the third power equals that. 2 to the third equals x squared minus 7x, which is 8 equals x squared minus 7x. This is a quadratic equation. Get 0 on one side. Factor and solve. I get two solutions to my quadratic equation. Now these are both solutions to my quadratic equation. But the original equation that I started out with was this one. It was a logarithmic equation. Now a quick glance says that 8's okay, because if you plug in an 8, you get the log of 1 and the log of 8. So that one's okay. But this one, you don't get very far in checking it, right? Yeah. Negative 1 minus 7, well, that's negative. So right there, you'd throw it out. Or even here, log of negative 1, throw that one out. So that one gets thrown out. This one, you can say, okay, well, at least it doesn't give me a negative number, and you hope that it's okay. If you did actually check it out, you'd end up with the log base 2 of 1, right? 8 minus 7 is 1, plus log base 2 of 8. Log of 1, any base, is going to be 0. What power of 2 gives me 8? 3. So it actually does check, if you wanted to check it out kind of completely there. All right, how are we looking on those? What I'm going to do now is give you kind of like a little mashup of different problems. We've solved exponential equations, we've solved logarithmic equations. Let's kind of bring them together and solve a little mix of both of those. We'll start with problem number 82. Let's take a look at that one. Are we okay with problem 56 before we move on? Good on that one? So problem number 82. Two log of x, so 2 log base 3 of x, I should say, minus log base 3 of x minus 4. X minus 4, yes. Equals 2 plus log base 3 of 2. Wow. Did I copy this down right? Someone double check me on that one. Let's see. X minus 4, 2. Yeah. Looking good. Okay. Now, as far as I'm concerned, we're probably going to have to use method 2 on this one. And the reason for that is because this is not part of a logarithmic term. Just no matter what you do there, you're not going to get rid of this 2 in terms of, being able to write it with a logarithm. If you could, and you can, but it'd be unlikely for us to do it at this level. So let's see what we can do on this one. Well, I can't start combining things here because I've got a 2 out in front. So let's take the 2 up here. That'll become log base 3 of x squared. And let's see here. Minus log base 3 of x minus 4 equals, you know what, I'm going to bring this to the other side. Minus log base 3 of 2 equals 2. So this one's going to get a little bit messy. And I won't give you one this hard, but try and follow along the individual steps. Our goal is to write this with one logarithmic term. That's our goal. And we practiced this last week. I probably should have done a little bit more work on this first step, but let me do it here. Let's do log base 3 of x squared plus log base 3 of x minus 4 to the negative first power. So I'm taking that negative up into the exponent here and here. It's probably the most convenient way to bring all these terms together. Remember, I want to write it with one logarithmic term. And the nice thing is that I can do that right now. I've got the log of this, this, and this. Yeah, we're going to multiply them, right? So that's going to be the log base 3 of x squared times x plus 4 to the negative first times 2 to the negative first equals 2. Now, just out of convenience, it's not necessity, but out of convenience, let's try and clean this up a little bit. Misfired. Do you remember what we did last week to clean up stuff like this? What did I do with these negative exponents? I put them in the denominator. So it's log base 3 of x squared over x minus 4 times 2. Wow. All right, sure. Let's distribute the 2. Why not? Log base 3 of x squared over 2x minus 4. Now, how about 2x minus 8 equals 2? I got the log of all of that. So, and this is what I wanted. I wanted to get down to the log of just one term. Now, as I promised, this is way harder than we're going to do on the exam. But the steps here are things that you should be able to follow, and I hope we can practice. We finally got it down to the log of something equals a number. Let's do step 2 now. What's it going to look like if we do step 2? Three squared. Perfect. So 3 to the second power. 3 to the second power equals x squared over 2x minus 8. 3 squared, of course, is 9. If I multiply both sides by the lowest common denominator, I get 9 times 2x minus 8. And on the right-hand side, that'll cancel. I get 18x minus 72 equals x squared. This is a quadratic equation. I'm going to move both of these to the right-hand side. 0 equals x squared minus 18x plus 72. And if you're having trouble with this one, I'll help you out. How about 6 and 12? What sign should I put in here? Negative and both negative. So I get x equals 6 and x equals 12. Those are my two solutions. Now, I'm not going to go through all the pain and torture of checking them all exactly, but what's the minimum we got to do? The minimum is we got to make sure that we don't have the log of any negative numbers, do we? If I put a 6 in here, positive, positive, that's already positive, so we're okay with the 6. How about the 12? Positive and positive. So, at least it passed the minimum test. I'm not going to try and actually go all the way through and plug it in directly. Both of those work. For those of you using Newton, let's do a problem that would come out of Newton. That would be something like this. Sung Lee invests $8,000 at age 18 in hopes it will be worth $32,000 when it turns 25. If interest compounds continually, approximately what rate of growth will he need to achieve his goal, round to the nearest tenth of a percent? On a problem like this, I'd probably help you out with this formula. A equals P e to the RT. And let's see what we can fill in from this one. What's A? Or how about, let's start with P. What's P? P is how much he invests initially, so P is 8,000. Good. P is 8,000. And now let's back up and see what's A. 32,000. Cool. So basically he wants to quadruple his money in 7 years. Good luck with that. So T is 7 years. R we don't know, but that's okay. We're trying to find R. So if I plug all that in, I get 32,000 equals 8,000 e to the r times 7. Now I'm going to rewrite that as 7r, but there's something else I'm going to do here to make my life a little bit easier. How about if I divide both sides by this 8,000? Remember, I want to solve for r. So if I divide both sides by 8,000, I'll at least get r a little bit more by itself. So 8,000, 8,000. Chris, what equation does that become? All right, 4 equals e to the 7r. Nice. Then what? How do we solve from here? This is back to your logarithmic equations, or exponential equations. Oh, very nice. Let's take the log base e, or ln on both sides. Log base e, log base e. Now, there's nothing wrong with writing it as ln. That's actually more appropriate, and you probably see the answer keys written that way. But why do I like writing it this way? What is it showing you? It shows you that it cancels, and what are we left with? 7r. How do you finish solving here? Divide by 7. ln of 4 divided by 7 equals r. Sweet. So let's see what kind of lofty interest rate he's giving himself, or needs. Keep in mind that current interest rate's probably around, like, you get 2% in the bank right now. That's pretty good. ln of 4 divided by 7. Woohoo! He's getting almost 20%. 19.8%. Man. If you can get that, tell me where I can get it reliably and safely, I'll give you extra credit. 0.198 blah, blah, equals R, so about 19.8%. Yeah, good luck on that. My mutual funds did half that good. I'd be really happy. Oops. What happened? There we go. Let's solve another one. Are we okay with this example from Newton? Let's do one from the book, kind of another exponential one. And let me give you this equation first. A of t equals p times e to the negative 1, or not negative 1, negative 0.000121 t. This tells you the decay rate of carbon-14. Has anyone ever heard of carbon-14? What do they use carbon-14 for? Carbon dating, radioactive carbon dating. So P is your initial amount. Let's start out with 100 grams. So if I put that in here, I have 100 e to the negative 0.000121 t. What I want us to do is figure out how much of this 100 grams approximately is going to be left after 5,730 years. So what you need to do, on your calculators of course, is plug in 5,730 here and give me a nice approximate decimal answer. It should round to something nice and friendly and even. And it's going to help us make sense out of the next part of this problem. Don't forget the negative out in front here, otherwise you'll be off a little bit. So if you round this off to the nearest tenth or so, you should get about what? About 50. So you start out with 100 grams, you end up with about 50. How's 50 compared to what you started out with? It's half. Yeah. So 5,730 is called the half-life of carbon-14. It's because, on average, that's how long it takes before you decay down to the point that you have half of what you started out with. And it's by this means that we can date things going back to maybe 40 or 50,000 years old. That's where carbon-14 starts to be a little bit more unreliable. But it's pretty cool. Let's see how that works. And I'm going to do a little bit of sleight of hand here and give you an easier version of this problem than is in the book. But it'd be more like what I would give you on an exam. So, let's see here. Carbon-14 dating. It says only 10% of the carbon-14 in a small wooden bowl remains. About how old is the bowl? So that'd be a problem that looks like this. 10% of what you started out with is what's left. So 0.10 equals e to the negative 0.000121 times t. And let's see if we can't solve for t. And I would give you an equation, something like this, to start. Suggestions. What could you do to solve here? Yeah, I'd take the log base e on both sides. So log base e of 0.10 equals log base e of e to the negative 0.000121 times t. We get some nice miracle simplification on this, especially on the right-hand side. How does the right-hand side simplify? T. T is our variable. T is time. So we don't know how old this is. But what we're trying to do is figure out how old this is. And there's one last step to figuring out how old it is other than doing it on your calculator. What's that last step? Divide by that, right? Divided by negative 0.000121 equals t. And let's see about how old this is. Now, radiocarbon dating is not as accurate as once was thought, but it gives us at least a ballpark. ln of 0.1 divided by negative 0.000121. Bam. So about 19,000 years old is about how old that is. So I think the limits of carbon-14, like I said, are around 40 or 50,000 years old. Then it starts getting a little bit difficult to date things with radiocarbon dating. You'd probably use potassium argon dating or something like that. Are we okay with this one? All right. Let's see. Let's do one last one, then we'll take a break. Problem number 90, part A. Log base 2 of x squared minus x. So log base 2 of x squared minus x equals 1. How do we solve this one? Method 2. So method 2 would be this to this power equals this. Let's do this one together. This would be 2 to the first power equals x squared minus x. Okay. 2 to the first equals x squared minus x. Move the 2 to the other side. 0 equals x squared minus x minus 2. That should factor. Who can factor that for me? X minus 2, x plus 1. Good. All right, x equals 2 and x equals negative 1. Got to check them. Should I throw out negative 1? Not necessarily. If you check it, let's check both of them. Let's check 2 to start with. If I plug in a 2, I get 2 squared, which is 4, minus 2 is 2. So I get the log base 2 of 2 equals 1. Well, that's fine, right? 2 to the first power is 2. All right, let's check the other one. If I plug in a negative 1, what's negative 1 squared? 1, so it's positive 1. And the negative of negative 1 is positive 1, so it would be plus 1. So now I'm log base 2 of 2 again. So they both check. So it's okay to have a negative number, you just can't take the log of that negative number. All right, I think we're due for a break.